Hello everyone. We are going to do the Cauchy Euler's equations. And these equations are going to be similar to what we've seen with constant coefficients, but we are going to have a simple variation of coefficients. So let me kind of show you that typical equation, how it looks. So it's going to be a x squared y second derivative plus bx y first derivative plus cy equals to 0. This is homogeneous equation, also called equidimensional equation. Why? The difference between equations we had before and this one is that in front of the second derivative, we have not only the constant a, but also function x squared. In front of the first derivative, we have x, and in front of the function, we have nothing. So coefficients are variables. Right now, it's ax squared and bx. C is still constant. So I'm going to write down that a, b, and c are constants. But x is going to x and x1, first derivative and the second derivative are power functions, right? Two power functions. So kind of a little difference between what we had before. So before we were looking for a solution in the form of e to the power of r, or like mu, or like exponential function, right? So what is going to be the difference over here? Well, exponential function is not going to work anymore, because remember when we were plugging in exponential function in all three terms, because exponential function, when you differentiate it, does not change the shape. We were able to manage the sum of these all exponential functions multiplied by some coefficient, which we could make equal to 0, which was giving us characteristic equation, which we used to find the actual power of e, right? Here, because second derivative is multiplied by x squared and first derivative is multiplied by x, it's not going to work, because at the end you are going to have exponential function by x squared, exponential function by x, and just exponential function, which are not going to be equal to 0 no matter what happens to the coefficients in front, right? They're just like linearly independent functions. But we can see that there is a function which is changing while you are differentiating it, but because we have additional multiplier over here, it can be compensated. You see, that's a power function and that's a power function, right? If you multiply them by other power functions, you can try to fit the power of everything to make it similar, like exponential function. Just here, when you differentiate, for example, power function, I'm going to write down for what type of a solution we look. We're looking for y equals x to the power of r. So it's not exponential function, but very close to it, right? And I think it's going to work. If you differentiate this, that's a normal power function, right? What is going to be the first derivative of it? The first derivative is going to be r e to the power, not e, sorry. Sorry, x to the power of r minus 1, and the second derivative is going to lose two powers, right? That's r minus 1, and r x, sorry, keep writing down the wrong stuff, and x to the power of r minus 2. You see that the second derivative is going to lose two powers, but because we have a multiple of x squared, it's going to fix these two powers back. And the first derivative is losing one power, and multiplied by x is going to return the power to the whole term to r. And the last one is not going to lose anything, so it's going to still have its x to the power of r. I'm going to plug in function first derivative and second derivative into the equation and see what we are going to get. And here, if we divide by x squared our equation, we're going to have x in denominator. And that means that we are going to have discontinuity. If we represent this equation in a standard form, which looks like this, y second derivative plus py first derivative plus qy equals, well, in this case equals 0, but equals g, actually that's a standard form of a second order equation. Both p and q are going to be not continuous at x equals 0. So we are going to consider x greater than 0, the continuity interval, okay? Why? Well, because we are dealing with power functions, and powers are not always going to be like natural numbers. Let's see how it's going to work. So I'm going to plug in all the derivatives, and I'm going to have a. And for the second derivative, I'm going to have it r and r minus 1. And r x to the power of r minus 2 multiplied by x squared is going to give me x to the power of r again, right? If I add up powers. And b r x to the power of r minus 1 multiplied by x. I'm keeping this x, which was a coefficient in front, I'm keeping it after the function, so you can easily see that it turns into x to the power of r. Well, the last one is going to turn into x to the power of r without any multiplication, just by itself. Oh, whatever I'm touching my touch board, it gives me these little dots, which I don't like actually. Okay. So now what we can do, we can use our standard approach, take x to the power of r outside and have a r minus 1 plus b r plus c equals to 0. Because we are searching for non-trivial solution, non-trivial not equal to 0 everywhere. Then we're supposed to have this factor equals to 0, because if this is not equal to 0, then this one is going to be equal to 0. Otherwise, we are not going to make up 0. And what we have in parentheses is called characteristic equation. It's just a typical quadratic equation. And r here is unknown, right? Because we were searching for the function y equals x to the power of r, but we don't know what is supposed to be r. Well, because it's a quadratic equation, I'm going to write it down. We also call it a characteristic equation or indicinal equation. I'm going to write down characteristic about r, right? So because it's a quadratic equation because the greatest power of r is square, right? We are going to get it from this term and from this term, multiply it. That's going to give us, well, I'm probably going to kind of write it down so you can see it's a quadratic equation. That's I r squared minus ar plus br plus c equals 0. If we combine these two terms together, we can have a r squared plus b minus ar plus c. You see, obviously, quadratic equation. What are options for quadratic equation? We already know from characteristic equation there are 3 options, right? We can have 2 real solutions, distinct, 2 real distinct roots. We can have 1 real root, which means that there are 2 roots, but they're not distinct. Or we can have 2 complex conjugate roots, right? 2 complex conjugate roots. Well, in all 3 cases, everything is going to look slightly different. So I'm going to start with the simplest case, and let me move to the next page. So case 1, 2 real distinct roots. I'm going to label them R1 and R2. So how solution is going to look? Well, remember that each root is going to have its own solution. Y1 is going to be what? X to the power of R1. And y2 is going to be x to the power of r2. They're going to be linearly independent. You can just kind of check it, but we are going to do it a little bit later. R1 not equal to r2. And the final solution, y, is going to look like the sum of y1 and y2, right? 2 solutions, and that's going to be c1 y1 plus c2 y2, which is going to give us c1 x to the power of r1 plus c2 x to the power of r2. So everything is simple, and eventually we're going to consider example, but let's talk about other cases. So case 2, 1 root. So R1 equals to R2 and equals, well, we say like R1, for example, or let's name it nothing, like R1 equals to R2. One root, I'm going to put it in parentheses. I'm going to write down the final answer and explain it a little bit later. So y is going to be equal C1 plus C2 ln of x. Looks a little bit strange. We never had ln before, right? Explain later. In the same lecture, just a little bit later. And case 3, complex roots. And I'm going to use notation lambda plus minus I mu. In this book, they are using alpha and beta. But I'm afraid that if I start using alpha and beta, eventually I turn back to lambda and mu. So when we have two conjugate roots, they're going to have a real part and imaginary part. Real part is lambda and imaginary part is mu. So how my solutions are going to look? Well, y1 is going to look like x to the power of lambda plus I mu. And y2 is going to look like x to the power of lambda minus I mu. There are going to be two solutions, right? Generally, each of these two solutions are complex. Remember situation when we were solving complex root for constant coefficients. And normally, in normal life, we have real value problems. So we need two solutions which are going to be real solutions. Each of these two is going to be complex solutions. And eventually, if you use them directly, when you plug in initial value for your certain equation, you are going to end up with a real solution. But if you want to generally write it down like a real solution, you will need to work a little bit on these complex conjugates. I'm going to start working with solution y1. So for y1, I'm going to write it down like x to the power of lambda plus I mu. And because the sum of the powers can be represented as a product, I'm going to write down x to the power of lambda by x to the power of I mu. Right? Now, x to the power of lambda is going to stay. But x to the power of I mu can be turned into sine and cosine, right? So the only thing that actually we don't know how to turn x to the power of mu. We know that e to the power of I mu is going to be equal what? Cosine of mu plus I sine of mu, right? But like x is a different base here, right? What I'm going to do, guys, I'm going to turn x into e. So what I'm going to do, I'm going to write down that x equals e to the power of ln of x. Is it true? Yeah. E and ln cancels, and we are going to get x back. How do I know that x is positive? Why don't I put absolute value around x? Well, because somewhere in the beginning I said that I'm going to consider only positive x's. So now I'm going to keep my x to the power of lambda. And instead of x to the power of I mu, I'm going to write down e to the power of ln of x multiplied by I mu. Now I can use my formula. Just my mu here is not going to be just mu, but it's going to be the whole thing like ln of x mu. So I'm going to have x to the power of lambda, e to the power of I, mu ln of x. So now the part which sits after I is going to be mu ln of x. And now I'm going to use Euler's formula and represent it as cosine of mu ln of x plus I sine of mu ln of x. And that's going to be my my solution. I'm going to do one more step here. I'm going to separate real and imaginary part of this solution. I'm going to multiply x to the power of lambda by cosine and x to the power of lambda by sine. So x to the power of lambda cosine mu ln of x, looks crazy, right? Plus I x to the power of lambda sine of mu ln of x. This is lambda, this is not x. Now guys, this is a real part of my solution, and this is imaginary part of my solution. Similar to what we had for constant coefficients and complex roots, remember that real part and imaginary part of complex solution are solutions by themselves if you have equation with real coefficients. And our equation is equation with real coefficients. So both imaginary part of solution y1 and real part of solution y1 are solutions of differential equation because coefficients are real. So at the end, you want to have like something real. So when you plug in the whole solution into your equation, you are kind of going to get like one parenthesis which is all real and one parenthesis which is all imaginary. It's supposed to be equal to 0, and we know that complex number is equal to 0. A plus bi equals to 0 only when a equals to 0 and b equals to 0. This way, imaginary part is going to make up its own equation and going to turn into solution. Okay, so what I'm going to do, guys, instead of using these two solutions, which are complex solutions, and then dealing with initial values and substituting everything, I'm going to just use a real part of my solution and imaginary part of my solution as solutions y1 and y2. So I'm going to write down that solution y1 is going to be, well, I'm going to write down the constant. Maybe I should write down just a whole general solution. Why should I do this? Why should I copy everything 3 times in a row? I'm going to write down y equals c1 x to the power of lambda cosine of mu ln of x plus c2 x to the power of lambda sine of mu ln of x. Somewhere here, I want to kind of point that this is x. Okay, now this is my solution y1 and this is my solution y2. They both are real, so the final answer is going to be a real solution. Now, as I promised, I'm going to return back to case 2. Case 2 is going to be long. That's why I saved it to the last part of the lecture. So case 2. Well, you remember what we were doing with exponential function. We were just multiplying it by t, and it gave us 2 independent solutions, and they both worked. It's not going to be as easy over here. And again, having same root, we are going to get just one solution, solution y1, which is going to be x to the power of r1. We'll need a second one. So the question is, what should we choose as y2? Well, I'm going to do some manipulations, and then I'm going to suggest your solution, and then we're going to just check it. But I want you to understand how we can logically come to this solution y2. You remember from previous lectures that if y1 and y2 are solutions, then the sum of them is solution and the difference of them is solution. Any linear combination of them is a solution, right? Let's consider a case when r1 is not equal to r2, but they are close to each other, are approximately equal. Approximately means that they're not identical equal, they're different a little bit, but they're very close to each other. So I'm going to build a solution which is going to look like this. Remember that y, c1, y1, and because they are not equal, we are kind of in case 1 right now. And we have c2, y2, like a linear combination of 2 different solutions. One is x to the power of r1, and one is x to the power of r2. How I'm going to create this linear combination? I'm going to say x to the power of r2 minus x to the power of r1 divided over r2 minus r1. You'll say, what kind of linear combination is this? It looks suspicious. Exactly, guys, looks suspicious, but let's see. What I did here, I did a difference of solutions and divided by a number r2 minus r1. Because they are not exactly equal, they're not dividing by 0. This difference is not 0. They're close, but not equal. And the top is not 0 too, because they're close, but not equal. And if you divide the first one by this, that's going to look like a constant, which is strange constant. That's 1 over r1 minus r2. And y1, the solution. And this one is going to be c2 constant is going to be minus r1 over r1 minus r2. Well, that finally fits into this, right? We know that it's a solution. Solution. What I'm going to do with this solution, guys, I'm going to let r1, r2 go to r1. So I'm going to consider a limit. What is going to be the limit of this solution? What is going to be the limit of y when R2 goes to R1? So here, x is kind of a constant temporarily, and the R1 and R2 are going to be the coefficients, the variables. So what I have, limit of x to the power of R2 minus x to the power of R1 divided over R2 minus R1, and R2 goes to R1. Does it remind you something, this formula? Actually, I want to change the color and write down the formula. You probably will recognize it. Yeah, guys, if I write down something like this, f prime equals limit f of x2 minus f of x1 divided over x2 minus x1. You probably recognize this formula. That's a formula of derivative, right? Generally speaking, in calculus, we usually write down this as h, and then instead of this, we write down h goes to 0. But when x2 goes to x1, that's going to be the distance between these two numbers, and that's, we can label it as h, and h goes to 0. And here, when x2 goes to x1, we are kind of bringing our secant line and make it a tangent line, right? If you compare this orange formula with green one, you're going to see, well, the formulas are identical, just the function is x to the power of r here. So we can consider that we have over here a derivative of a function of x to the power of r. But in this function, x considered as a constant, and r is a variable. Do we know the derivative of x to the power of r if x is a constant and r is a variable? Yes, we do. I'm going to write it down. If I want to differentiate x to the power of r differentiated by r, I'm going to put here r showing that r is my variable. What can I do? I can use my standard approach, e to the power of ln of x multiplied by r, and then differentiated by r. Remember, the derivative of exponential function is what? Exponential function itself, multiplied by derivative of, like, when it's composition, the second function inside, right? Here, if ln of x is a constant, then we are going to have like a constant multiplied by r. If we differentiate it, we are just going to have ln of x here. We're almost done. That's not going to take any longer. So now we can say that back, this one is x to the power of r, and that's going to be derivative. Derivative of x to the power of r, it's actually x to the power of r by ln of x. So here, I'm going to have actually what? X to the power of r ln of x, and it's going to be r1 actually here, right? Because it was r1 where we were going. It's not going to be general derivative. So I'm just using a derivative, the explanation. Now, now I'm just going to have my second solution, because this solution is different or not equal to x to the power of r1. If you compare them, they are totally different. This doesn't look like 1, right? It looks like point. So I'm going to use it as my y2. So my solution then is going to be y equals c1 y1 plus c2 y2, and that's going to be c1 x to the power of r plus c2 ln of x to the power of r. And what I did when I was explaining or introducing it, I took x to the power of r outside. So that's x to the power of r, and you can write down c1 plus c2 ln of x. You don't need to do all this explanation every time when you need to write down a solution. Actually, we do it once and use it as a proof something. And now you can just use it as a ready formula. If you have a same root, you are just kind of using the formula for it with ln. Okay, so very good. Now the question is, well, we did these manipulations with the derivative, a little bit kind of tricky, right? Is it going to work actually? Is this a solution? If this x to the power of r1 and multiplied by ln of x is a solution, I want to actually check it. And you guys with me, if you don't like to check it, okay, skip this part. Check that y2 x to the power of r ln of x is a solution. Well, what we need to do the check, we just need to differentiate it once, and that's going to give us r x to the power of r minus 1. Because it's a product of two functions, I'm going to differentiate the first one, and then I'm going to differentiate the second one. And I'm going to get x to the power of r minus 1, r ln of x plus 1. You see, I kind of got this x. The first derivative was losing 1 power. And I'm going to do the second derivative. Give me a second, guys. I'm going to move this. I don't want to actually move. I'm going to move this up so we can write down in the bottom. So here we're going to differentiate. Yeah, expression is going to be long, but worth to check it once, right? So I'm differentiating the first expression again. It's a product, so it's going to give me two terms, r minus 2 ln of x plus r x to the power of r minus 1 over x derivative of ln, right? Plus r minus 1 x to the power of r minus 2 differentiation of the second term, which is just like a term. And I don't know, maybe we can just use as it is, do not simplify it. But you see that all powers of x here is r minus 2, and this one is going to be r minus 2 when you kind of divide by this x. So good to see, right? Maybe I should simplify it. So I have r minus 1 ln of x plus r minus 1. And here x r minus 2. I'm taking r minus 2 everywhere. And this one is going to give me 2r. Maybe I should just write down 2r instead of kind of copying everything 2 times. So let me erase it. And doesn't want to go. 2r minus 1, right? Good. Now I'm going to plug everything into my original equation with x squared and other stuff, right? Okay, it's not going to be very simple, but let me change the color. So it's kind of looking differently. Blue. So I have a x squared and this x r minus 2 from the second derivative, and that expression r minus 1 ln of x plus 2r minus 1. Okay, first term. The second term, bx, and for the first derivative I have, why don't I put this x to the power in terms? X r minus 1, I'm writing down this one, r ln of x plus 1, and the last one is going to be just cx, sorry, I keep writing down something wrong, x to the power of r ln of x equals to 0. Is it going to be equal to 0 or not? Depends on like whether it's a solution or not, right? So now what I see that this one is x to the power of r, this one is x to the power of r, and this one is just x to the power of r. So we can take it outside, and my what is inside of parentheses is going to be a r minus 1 r ln of x plus a 2r minus 1. I'm just opening parentheses a little bit, plus bx r ln of x plus b. Oh, no, there is no x, sorry. I already simplified it. I'm just not supposed to copy it second time. Let me erase this one. Let me erase the whole thing and just write it down correctly. So I combined this x already, so it's br ln of x plus b. All right, b multiplied by 1. This one is combined and outside of parentheses already. Plus c ln of x. So I'm going to combine terms with ln first, and unfortunately I'll need to go to a different page. Terms with ln are this. I think I should close, write down 0 here. So I'm going to combine the first. Let me move to a different page and keep x to the power of r outside of parentheses. So I have ln of x, ar, r minus 1 plus br plus c. These are terms with ln, right? Plus terms without ln, a, 2r minus 1 plus b equals to 0. So this is going to be equal to 0 because r1 is a root of characteristic equation, which is actually same, a r r minus 1 plus br plus c equals to 0. The question is, what about this? Is it going to be equal to 0 or not? I'm going to write it down separately. A 2r minus 1 plus b, is it equal to 0? Well, if we like simplify this equation and turn it into quadratic form, we are going to have what? That's going to be a r squared plus b minus a r plus c equals to 0. If you do have just one root, then r equals minus b minus a over 2a, right? Which is a minus b. I'm turning this minus in front, 2a. So that's a root. Now, what do we need to do? Just take this root and plug it in, because that's going to be my R1, right? If you have just one root. And see if it turns into a true statement or no. So a 2 and a minus b over 2a plus b equals 0. Is it equal to 0? Well, 2 and 2 cancels, a and a cancels. And I have a minus b plus b. I think I'm missing something. Yeah, I forgot about minus 1. There was minus 1 here. I have to read now this part and to write down minus 1. Minus 1 here in parentheses. Sorry. And I have to erase next line too, because I already kind of started using wrong expression. So yes, everything cancels over here, but a is going to stay here, right? Again, something wrong. So I'm going to start with this term. So 2 cancels, a and this a are going to give me kind of 1. So I have a minus b. This minus 1 is going to be multiplied by a and give me minus a. There is no denominator, so just multiplication, and plus b. You see it equals to 0. So a minus a, b minus b equals to 0. So it's a solution. I'm going to write down. It is a solution. Okay, good. So we kind of proved everything. Now we are going to do examples. Let me see. Okay. Maybe use a different color. Examples. We're going to start with first example, 2x squared y second derivative plus 13x y first derivative plus 15y equals to 0. Build characteristic equation. We see that it's equidimensional, second power of x, second derivative, first power of x, first derivative, no power of x, no derivative. Right, we have 2 and r minus 1r plus 13r plus 15 equals to 0, which is going to give us quadratic equation 2r squared plus 11r. I'm simplifying everything, plus 15 equals to 0, which is going to give us r1 and 2 equals plus minus square root of 121 11 square, right? Minus 2 by 15 by 4 minus 11, kind of crazy, divided over 4 because it's 2 over here, right? Which is going to give us minus 3 and negative 5 over 2. Well, here 121 minus what? 30 by 4, 120, so it's 1 actually, right? So we have 1 here, plus minus 1, minus 11. And I don't want to write everything like 10 times, so 11 minus 11 plus 1 is going to give us minus 10 over 4. It's minus 5 over 2, right? Minus 11 minus 1 is minus 12. If you divide by 4, you are going to get minus 3. So solution is, let's say, c1 x to the power of minus 3 plus c2 x to the power of minus 5 over 2. You can write it down c1 over x cubed plus c2 over x to the power of 5 over 2. Don't forget that x here is greater than 0. Very simple, right? Almost user-ready formula. Okay, example number 2. X squared y second derivative plus 5x y first derivative plus 4y. I'm thinking that's going to be a complex solution. No, that's going to be one real root. So characteristic equation r minus 1 plus 5r plus 4 equals 0. Remember that we are searching for a solution as x to the power of r. And simplifying this equation is going to give me r squared plus 4r plus 4 equals to 0, right? Why? Because I have minus r here, it's 4r. Well, obviously, a solution is r equals minus 2, right? That's a perfect square, and 1 root. And I'm just going to use my formula for ln, right? I'm just going to write down y equals c1 plus c2 ln of x by x to the power of negative 2. You can put negative 2 in the denominator, and that's going to be something like a fraction without negative 2. But otherwise, again, don't forget to mention that x is greater than 0. And just last case is left, case number 3, which is going to give us complex solutions. And that's going to be r minus 1 plus r plus 4, right? Again, I'm searching for a solution x to the power of r. And if you multiply everything, you are going to have r squared plus 4 equals 0, which is going to give you r equals plus minus 2i. So there is going to be no lambda, no real part, but mu is going to be equal to 2. So you just can write down the ready solution, y equals c1 cosine of 2 ln of x plus c2 sine of 2 ln of x. You're supposed to have x to the power of lambda here somewhere, but because lambda is equal to 0, it's x to the power of 0, which is going to be equal to not 0, but 1, right? X to the power of 0 is 1. Okay, now just one little question. What should we just learned how to solve homogeneous equation. What if equation is not homogeneous, but non-homogeneous? So I'm going to write down DE is non-homogeneous. Well, I don't know. For example, we have a very same equation. We had an example 1, but with the right side, like 2x squared, y second derivative plus 13x, y first derivative plus 15y equals to 0. And my solutions, remember, were 1 over x cubed. Sorry, it doesn't look like x cubed. I'm going to just rewrite it. Solutions were y1 equals 1 over x cubed, and y2 was 1 over x to the power of 5 over 2. So how do we solve if it's non-homogeneous? That was homogeneous. I'm now going to change my color and make it non-homogeneous. Yes, what kind of non-homogeneous? Well, just let's use a power function. For example, x to the power of 3. So how would we solve it? Well, here, guys, we are very lucky because we have a power function and my general solution is a power function. So suggestion is to look for a particular solution in the form of ax to the power of 3. Why? Because we'll need to make sure that the left side of my equation, after I plug everything in and differentiate everything, is going to give me a same power here. But I do know that this one is not differentiated, so it's supposed to be same power originally. So I'm using a cube here. And let's see how it's going to work. So again, as a guess, maybe it's not going to work, but probably will. So derivative y particular solution is going to be what, 3ax squared, and the second derivative is going to be 6ax, right? Now plug into equation, we have 2x squared, 6ax plus 13x, 3ax squared, and 15ax cube supposed to be equal to x cube. Again, I just made it up. I did not use anything from the book. I think in the book they even don't consider no homogeneous case. Now, guys, what we have, x squared and x is going to give us x cube, and x cube. So we can take x cube outside. We have 12a plus 13 by 3a and plus 15a supposed to be equal x cube. Well, these are just numbers. We can adjust a and make it equal to x cube. So x cube we have on this side too. So what is 12 plus what? 39 plus 15. I think it's 66a, supposed to be equal to 1. And we have a equals 1 over 36. So my solution, particular solution, is going to be 1 over 66x cubed. And the general solution of this equation is going to look like c1 over x cubed plus c2 over x to the power of 5 over 2 plus 1 over 66. Not 166, but 66. 1 over 66 x cubed. Well, we were lucky here because we kind of used undetermined coefficients because it was a power function, right? Whenever you have a power function, it's going to work. But if anything more complicated happens over here, you will need to use variation of parameters. I'm going to just set up an example, but I'm not going to solve it. It's going to take like another half an hour, and we are already working for like an hour. So if we have the same equation, something like this, 2x square y second derivative plus 13x y first derivative plus 15y, and it's not equal x cubed but equals e to the power of x, for example, you will need to use variation of parameters. When you do it, don't forget that variation of parameters is a standard method, but you will need to bring your equation to a standard form. Standard form is y second derivative plus p y first derivative plus qy equals like g, right? Remember? So here we'll need to divide by 2x squared to get it. So y second derivative plus 13x over 2x squared y first derivative plus 15 over 2x squared equals e to the power of x over 2x squared. Well, you can do cancellation, but otherwise that's going to be it. So equation is going to look like this. So we cannot touch it. Y second derivative plus 13 over 2 y x y first derivative plus, I forgot y here, 15 over 2x square y equals e to the power of x 2x squared. And we do know solutions of homogeneous equation, right? They're still saying y equals 1 over x cubed and y2 equals 1 over x to the power of 5 over 2. So remember, equations are kind of for variation of parameters. Variation of parameters are same. That's c1 prime by the first function, y1 plus c2 prime by y2 supposed to be equal to 0 because derivative does not change, and c1 prime y1 prime plus c2 prime y2 prime, and they are y1 and y2 happens over here, equals e to the power of x 2x squared. And you just solve them. And sometimes you won't be able to solve them because integrals are too complicated. Then you can leave everything in integral form. Well, I think that's all. In the homework, you have no non-homogeneous equations, only homogeneous equations are given. But for fun, you can try to solve this one. I actually did not solve it, so I don't know the answer. But if you do it, I'll give you some extra credit points. Okay, that's all. And I think I'm going to stop this lecture at this point and see you all later.